So next, let's look into the next level, which is RAID level 1, which is a slightly advanced version RAID configuration compared to the baseline case RAID 0. RAID 1 is also called mirroring or mirrored disks, whereas RAID 0 is called striping, non-redundant striping. Okay, so let's see how it works. Mirroring, so what does it mean? RAID 0, RAID 1 means it keeps exactly the same data twice. 2 copies of each piece of or each block of data. So if you take a look at the example shown in this slide, at the top level, it shows the logical blocks. It maintains a total number of 4 logical blocks. And the bottom level shows the physical data layout. Okay, so the physical layout, the data spread across 2 physical disks, namely disk 0 and disk 1. And the same data block gets duplicated, gets stored exactly twice. So 0 stored once under disk 0 and stored the second time under disk 1. That's the same for the rest of the 3 blocks. So this is called mirroring, which is easy to understand. So again, let's revisit this failure or reliability assumption. Assume disk failures. A failure model follows a fail-stop model. And within a typical fail-stop model, we're only looking at 2 different states. One state if the system works, and the second state if the system simply don't work, the system fail, crash, due to whatever reason you name it, right? The software failure or the hardware failure, but it just simply failed, okay? And we know another assumption, sub-assumption under this is we know exactly when they don't work. Assume we know they don't when they don't work, okay? And this is the failure assumption. Keep that in mind. So let's see how RAID 1 mirroring works. Again, we use this 4-disk configuration example. In this example, we have the disk 0 to disk 3, a total number of 4 disks, and assume we're using mirroring, meaning the same data block gets stored twice, gets duplicated one more time. So the same chunk of data, let's say 0, gets duplicated a second time under its neighbor disk, which is disk 1. And the same for the rest of the data blocks, okay? For example, disk 1 gets, block 1 gets duplicated once among disk 2 and disk 3, okay? So in this case, if you're talking about the reliability model or failure analysis, the question is, how many disks can fail? So, or how many failures can RAID 1 configuration tolerate at most, right? So there are 2 answers, and each one of these, either one of these 2 answers, it depend by different cases. So we have a best case scenario. The best case scenario is if the failures happens to non-neighboring disk, non-adjacent disks, or right. So let's say if there are 2 failures, and these 2 failures happen at the disk 0 and disk 2. These 2 disks gets failed. So we basically lose one single copy of all the data that gets stored in this configuration. We lose this offset and we lose these disk. But again, we have disk 1 and disk 3, which still store the unique data without losing any data. So the best case scenario, it could tolerate at most 2 failures. Okay, but this is only the best case. Worst case is, let's say instead of let me erase this. Okay, so the worst case. So instead of having non-adjacent disk fails, let's have two neighboring disk fails. So in this case, unfortunately, disk 0 and disk 1 fails. That means whatever data stored within disk 0 and disk 1, the first two disks, they're all lost. They're all gone, okay? So basically half of the data gone. 0, 2, 4, 6 data blocks are totally lost. And we have, even though we have the second half of the data safely stored at disk 2 and disk 3, but basically you lose half of the data, which is undesirable, right? So the worst case is we don't want this kind of situation to happen. So that means two failures we cannot tolerate. It cannot tolerate two failures, but instead it could only tolerate, can only tolerate one single failure. So at any single point of time, the worst case scenario is the mirroring example, the mirroring configuration, or the RAID-1 could only tolerate one single failure, okay? One single failure at a time, okay? So this is a common case. So we need to use the worst case as a lower bound. So this is a reliability analysis. So let's take a look at the other analysis for the other metrics. First of all, is capacity metric. This is straightforward, right? So again, N is the total number of disks involved, and C, letter C represent the capacity supported by each disk. It could support at most N times C divided by 2, this much data, because we're talking about redundancy, and each unique piece of data is stored twice. So that's why we have the factor of 2. Basically, it cut half effective capacity that could be used to store unique data. And the reliability is 1 or maybe, we have a maybe over here, N divided by 2. Assume N is 4, 4 divided by 2 gives 2. But this is only the best case, right? So most of the time, we're not talking about best case. Best case is if we have luck. But unfortunately, under the best case, under two failures, the chances are it could lose half of the data. So this, to be on the safe side, a more conservative analysis of the failure model, the reliability analysis, is RAID-1 is only able to tolerate one single failure. Okay, so this is important. This is really important. You cannot just say it tolerates N divided by 2. This is, you know, the optimistic case. Let's use optimistic. Okay. Pessimistic is it could only tolerate one single failure. So let's next take a look at the performance. Let's first take a look at throughput. For sequential read, sequential write, divided by a factor of 2, right? So why is that? Let's first talk about sequential read, sequential write. Okay. So we have disk 1, disk 2, disk 3, disk 4, 0, 0, 1, 1, 2, 2, 3, 3. Okay, redundancy. So the sequential read. So it could read this whole. It could read this whole stripe. It could read this whole stripe in one go. It could read this whole stripe in one go, right? So this is sequential read. But in fact, effectively, we're only reading out half of the whole data that get read out as unique piece of data, which is 0 and 1, 2 and 3. So that is why we need to consider this factor of 2. So the whole sequential read or sequential write bandwidth gets effectively cut half, right? Because of the redundancy. If you take a look at random read and random write, so let's first take a look at random read. Random read is fine. Random read means there are just multiple concurrently issued random small read operations. It can't happen to this one. It can't happen to this one. It can't happen to any one of these, right? So that means for random read operation, it could effectively utilize all of these n disks. And in this particular case, n is equal to 4. All of these 4 different disks. So the random read performance is n times r. For random write, it's a different story, right? So how to support random write? For random write, so let me use a different color. Let's use this orange color. For random write, so each random write gets translated into 2 physical write operations. So let's say if you want to random write to this disk block number 6, this logical write operations gets translated into 2 physical writes because it stores 2 copies of the same data. If you want to update this 6, you have to update this 6 as well on disk 2. So that is why you need to consider this factor of 2. So that is why it's n divided by 2 times r, where r is the random throughput that could be sustained by a single disk. Okay? So next, let's take a look at latency. Latency, again, the same. So latency, recall D is the latency to serve any single outstanding random small IO, no matter whether it's read or write. So this single latency is still D. Okay, this is easy to understand. So that completes the second RAID configuration, which is RAID-1 or mirroring.